Alright folks, this video is going to be on titrations. So in a titration, what typically happens is a solution of known concentration. So we know the molarity of the solution, and we can figure out the volume that we need to add. So this is the known concentration, is titrated against an unknown solution of unknown concentration. Right? In terms of acids and bases, you would either have one known acid and an unknown base, or a known base and an unknown acid. Now, you're going to titrate those things against each other until you reach an equivalence point. So this is the point at which the reaction is complete, but it's also known as the point in an acid-base reaction where the moles of hydroxide are equal to the moles of H+, or hydronium. Now, an indicator is used to indicate when that equivalence point takes place. So the indicator is typically a weak organic acid or base that changes color at or near the equivalence point. So at a specific pH, it will have a characteristic color change. That's why it is called an indicator. What you've seen thus far this year is a titration of a strong acid and a strong base with the indicator of phenolphthalein. It has a characteristic pink color when it's in basic solution. And so in your previous titration this year, you took a known base, and you put it in the burette of known concentration, and you added it to a solution of unknown acid but known volume until you got that faint pink indication that the equivalence point has been reached. Now that indicator shows us that the moles of hydroxide are equal to the moles of H+ or hydronium in this titration. An alternative method for equivalence point detection, or just alternative method for mapping out titrations, is a pH meter. All right, and so we'll be using one of these this year as well. So let's talk about different types of acid-base titrations. Let's first start off with the strong acid, strong base titration. So strong base being sodium hydroxide, a strong acid being hydrochloric acid. And they result when they neutralize to form water and the salt NaCl. Now the net ionic for this can be written as such right here. Now one thing to point out is, being that they're both strong in nature, and it's just, units of hydroxide being added to units of hydronium, you can see that as NaOH is being added, so this line indicates how much NaOH is being added, the pH, as you add it to the acid, the pH goes from a low value, and there's a sharp spike upwards. All right, now within this sharp spike upwards is the equivalence point, where the number of moles of acid equals the number of moles of base. And in a strong acid-base titration, this equivalence point is at a pH of 7. When the number of moles of each are equal, the pH is neutral. So that's a strong acid-base titration. The next type of titration is a weak acid, strong base titration. Right, so this is a weak acid, strong base titration. Now you can think acetic acid right here, and this is sodium hydroxide. You titrated them against each other, that would be a weak acid and a strong base. Its net ionic equation is written as such. Now, one thing to know about a weak acid, strong base titration is at the equivalence point, the pH is going to be greater than 7. Right? Right, when the number of moles of weak acid is equal to the number of moles of strong base, all of the moles of strong base that are involved will go to work and dissociate, whereas only partial amount of the moles of weak acid will do the same thing. So remember, with weak acids, you have only partial ionization and partial behavior of acids, and the rest of it will be the work of its conjugate base. So because acetic acid doesn't fully neutralize, it also has its conjugate base working with water to produce hydroxides. At the equivalence point, you're going to see a pH at the equivalence point of weak acid strong base titration. You're going to see a pH greater than that of 7. So a known volume of NaOH is added to an unknown of the weak acid. And at the equivalence point, you have a pH greater than 7. That's a characteristic of a weak acid strong base titration. So let's work through a problem, all right? Let's work through a problem with a weak acid strong base titration. So we're going to calculate the pH in 3 points of this titration, titrating 25 milliliters of known acetic acid. So let's add 10 milliliters of the NaOH. Now in the reaction, there's 1 mole of acetic acid for every 1 mole of NaOH, so there's one equivalent of each. That will be important when we work with acids and bases with different equivalents. So at every stage of the titration, we can calculate the number of moles of base reacting with the acid. Right? And the pH of the solution is determined by the excess acid or base left over. But the pH being that you're dealing with weak acid here, it'll depend on the extent of hydrolysis of the salt formed or the hydrolysis of the conjugate base of the weak acid. All right, so let's first the number of moles of NaOH in 10 milliliters. In that first instance where we add 10 milliliters of the 0.1 molar NaOH, we had this many moles of NaOH reacted. Now the number of moles of acetic acid originally in solution is this. Right? Once again, we're working with moles at this point because as you add volume to the solution, molarities are going to change, but the number of moles of each species will not. So we're going to work with moles instead of molarity in this case. So if you add this many moles of NaOH, all of it being a strong base will react to leave this much weak acid left over. All the base will react, leaving nothing left, and you will form 1 mole of the salt for every mole of the strong base used. So at this stage, we've made ourselves a buffer system of acetic acid and the acetate ion from the salt sodium acetate. So to calculate the pH of the solution, use the Ka of acetic acid, the Ka of acetic acid, and solve for the H plus concentration. You know the concentration of the acetate ion, the conjugate base. You know the concentration of this acid. Plug those all in to give yourself an H plus concentration. Therefore, the pH is, taking the negative log of that H plus concentration, is 4.57. So now let's do when we have equal amounts of moles of both acids and bases. When there's 25 milliliters of 0.1 NaOH, sodium hydroxide, reacting with 25 milliliters of 0.1 acetic acid. This is the number of moles of sodium hydroxide. That is the original number of moles of acetic acid. All that acetic acid will react. All the sodium hydroxide will react. And you'll have nothing but the acetate ion. Okay, you'll have nothing but the acetate ion. But you do have to take into account, okay, the concentrations of both the acid and base are 0. The concentration of the salt is this. We have to factor in how much the acetate from, so the conjugate base of acetic acid, in the form of this salt, we have to factor in how much this is going to change the pH. Now, it does that by undergoing hydrolysis. So this acetate ion will go back in, The acetate ion will go back in and reform some of the acetic acid and increase the concentration of hydroxide in the water. Now, we looked up the Kb for the acetate ion in table 15.3 in your book. Kb is right there. We plug it into this expression, and we solve for x to get our hydroxide concentration. From having the hydroxide concentration, you can figure out the H plus concentration, and therefore the pH. The pH is going to be 8.72. Now, after the addition of 35 milliliters of sodium hydroxide, this is at the point in which you have excess strong base and all of your weak acid has reacted. So the amount of moles of strong base is 3.5 times 10 to the negative 3. It's going to react with the entirety of the moles of acetic acid. So all of these moles are going to be used up. There's going to be no acetic acid left. But you'll still have 1 times 10 to the negative third moles of sodium hydroxide left, along with 2.5 times 10 to the negative third moles of sodium acetate, including that acetate ion. We have two species in the solution that are responsible for making the solution basic at this point. That's hydroxide and the acetate ion. But because the hydroxide is much stronger, OH is much stronger than the acetate ion, we can safely neglect the hydrolysis of the acetate ion and just calculate the pH based off the excess concentration of hydroxide ions. All right? And so the total volume of the combined solution, this is from the acid solution, and this is from the sodium hydroxide solution. That's going to be 60 milliliters. So we take the number of hydroxide moles left over, divide by 60, multiply by 1,000 to get our new molarity of hydroxide. Taking the negative log of that molarity of hydroxide, right here, negative log of that molarity of hydroxide. We'll get the POH. From the POH, we subtract from 14 to get the pH. So that's our pH of the next solution. The next type of titration that we can go over is a strong acid, weak base titration. A strong acid, weak base titration. An example of this is hydrochloric acid in a solution with the weak base ammonia to form ammonium chloride. So the net ionic would be H plus the ammonia. It's going to be ammonium. So chloride is left off in the ionic equation. Now, at the equivalence point, where the number of moles of strong acid and weak base are equal, the pH is going to be less than 7. Why is that the case? Well, the strong acid will completely dissociate and break apart. And the weak base will have some of itself acting as a weak base, but its conjugate acid, ammonium, will also be reacting with water to increase the concentration of H+, as you can see here. So with a strong acid, it completely reacts, its conjugate does nothing. But the weak base, the base acts like a base, but its conjugate here also acts in the reverse direction as an acid. Okay, so we're adding HCl to a solution of base. It starts off very basic, and it continues and continues and it continues. You're going to see a sharp decline at the equivalence point, but you know this is a strong acid weak base titration because the pH at the equivalence point with a number of moles of each species, the strong acid and weak base, the number of moles is equal. The pH is going to be less than 7. It's going to have an acidic pH. So let's work through example 16.6, all right? We're going to calculate the pH at the equivalence point when 25 milliliters of 0.1 molar ammonia, NH3, it's a weak base, is titrated by 0.1 molar hydrochloric acid, the strong acid. So we can write the reaction as such. Now, this will be important in later titrations, but for now, we know that there's a 1-to-1 equivalent. For every 1 mole of weak base, there's 1 mole of strong acid. So at the equivalence point, the major species in the solution are the salt. All right, it's the ammonium chloride, water. So let's look at what this ammonium chloride salt at the equivalence point will do to the pH. So the total number of moles of ammonia is calculated here. And at the equivalence point, the number of moles of HCl is equal to the number of moles of water. HCl will completely react because it's a strong acid, completely reacting with the base, leaving only the formation of 2.5 times 10 to the negative 3 moles of ammonium chloride. So all that's left at equilibrium is ammonium chloride, which is the conjugate acid of ammonia, the weak base, and it will undergo hydrolysis. All right, so let's figure out the molarity of this ammonium chloride. The total volume of the acid and base added together is 50 milliliters. So if we take the number of moles of this salt, ammonium chloride, that exists, divided by 50, multiply by 1,000, we have a 0.05 molar solution of the salt. So the pH of the solution is dictated by the hydrolysis of those NH4 plus ions, the conjugate acid of the weak base ammonia. So this conjugate acid initially has this concentration. It's going to hydrolyze and decrease in concentration by some factor of x, and increase by concentration by the same factor of x. You plug in the Ka expression for the hydrolysis of this weak acid, solve for x using the approximation, and solve for the concentration. Solving for x will give you the concentration. See, H plus, once you solve for x, you get the concentration of H plus in solution. You take the negative log of that, and then you get the pH of the solution in this titration. All right, so qualitatively, you can check that the pH of the solution is acidic. You had a strong acid and a weak base. So you would think that, yes, qualitatively, this reaction at the equivalence point would have an acidic pH.